the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is meant for linear algebra students who are currently going through matrix equations. You've already gone through vector equations and row reduction methods, and you know everything you need to know about linear systems. And specifically in this video, we're just going to go through this one theorem and we're going to prove it. And it's kind of important to pay attention to this proof because it really does showcase what you want to do as you move forward in mathematics, how you want to build proofs. So let's familiarize ourselves with this theorem first. The theorem states that the matrix equation AX equals B has a solution if and only if B is a linear combination of the columns of A. This is, again, one of those theorems that as you move through linear algebra, some of these theorems that come up, you just think, man, haven't we already said this? It does feel like that at times. I would 100% agree with you if you felt that way. The textbook that I use, the author takes his time going through and really slowly introducing you to massive concepts. And so because of that exposure, you do really get a natural feel for why this is true or that this is true. However, you haven't had this formal statement until this point. One thing I do want to note here, and if you've already seen one of my proofs in the past for an if and only if, please forgive me when I say this, an if and only if is a bijection. It basically means that the first claim, which is called, honestly, the antecedent, in the first part of this theorem, our claim, we're just going to call that P. So the claim P is that the matrix equation AX equals B has a solution. The claim Q is that B, the vector, is a linear combination of the columns of A. That will be our claim Q. So in an if-then statement, if P is true, then Q is true, P is called the antecedent and Q is called the consequent. However, with an if and only if, this claim goes both directions. That is, it goes this direction, if P then Q, but it also goes the other direction, if Q then P. So Q is simultaneously the consequent and the antecedent. And likewise, P is simultaneously the antecedent and the consequent. So when you do a proof of an if and only if, you actually have to prove both directions. You have to prove what we would call the forward direction and the backward direction. So the forward direction is if P then Q, the backward direction if Q then P. So let's go ahead and structure our proof right now. It is very common that when you're doing an if and only if proof or a proof for an if and only if statement, that you let the world know which direction you're starting with. So it is very common in mathematics to see somebody write that, which means they're proving the forward statement. If the matrix equation AX equals B has a solution, then the vector B is a linear combination of the columns of A. So let's focus on that proof first. We're going to suppose that the matrix equation AX equals B has a solution. Now what we're going to do is just take a look at where we want to arrive. We want to arrive at the fact that the vector B must therefore be a linear combination of the columns of A. And if we want B to be a linear combination of the columns of A, we somehow need to go from a matrix equation to a vector equation. And this is where I generally say you should think about all of the theorems that you've learned up to this point in your linear algebra course, or actually in all of your courses. Initially, I recommend that you have some type of theorem list or a list of theorems that you've learned. But as time goes on, you're going to erase some of these theorems from this list because they're going to become so natural for you to remember. For example, you may never need to write down that row operations are invertible because you just naturally know that after a while. You know that that's a theorem, you know that you use that, you know that it's true. And so after a while, you can start removing some theorems from this list so they don't clutter your list of theorems that you've learned. Some of these They're not inconsequential, but they get used less frequently than others in theory. Now, I'll just say right now, if I scroll through this list of theorems, none of them are going to be applicable to what we're discussing right now. And the reason why is these are theorems that we have introduced prior to getting into the section of the textbook that I'm currently lecturing out of. Since we've entered the section that I'm currently lecturing from, we've learned some extra theorems that are not in this list. So let's look at our nearest neighbor theorems, our theorems that we've most recently learned. And here's a theorem we recently worked on in a video not too long ago where we did partial proof of. And this theorem specifically states that the solution set for a matrix equation is the same as that of the associated vector equation. So if I know that ax equals b has a solution, then its associated vector equation must have the same solution. And I'll quote that here. And I state it this way by Theorem 3 because in the textbook that I use, that's actually what that theorem is called. It's called Theorem 3. It's just a reference number so that you can refer to it in proofs and stuff like that. However, if you're working out of a textbook that doesn't number that theorem, you could say by a previous theorem, we know that the vector equation x sub 1 a sub 1 plus x sub 2 a sub 2 plus so on and so forth, all the way to x sub n a sub n is equal to b, has the same solution. Now, when you get to this point right here, it is kind of important to note because you made no claim about what x is or how many terms there are or elements there are in x, and you never made a claim about the structure of the matrix A. You might want to say something about that structure right now so that people know what you're referencing when you say vector A sub 1, vector A sub 2. So I might say, I'll put a little star on here, and maybe off to the side, I'll just put a little note for the reader. So in this note here, I just basically said A is an m by n matrix. In other words, we just don't know how many rows or columns there are, but we're going to assume the structure is that we have n columns, so our column vectors are going to be labeled A sub 1, A sub 2, all the way to A sub n. And for the matrix vector multiplication to be well defined, X itself has to have the same number of entries as columns of A, so X will have to be an Rn, and then B from the matrix equation definition has to have the same number of entries as rows. And by the way, I didn't write it here, but also the column vectors here are also in Rm because, well, each column has m rows, so each column vector has m entries. Not that big of a deal for that last part, but just thought I'd mention it. All right, so where are we in our proof? Suppose that our matrix has a solution, then the associated vector equation also has the same solution. Where do we want to arrive at? We want to arrive at the fact that B is a linear combination of the columns of A. Now take a look at this. This result right now almost tells us that B is a linear combination of the columns of A. That is, B is the sum of scalar multiples of the columns of A. I'm not telling you that X is the solution. That is not what I'm saying. I'm saying there is something I can plug in for the vector X that will be a solution to that vector equation and to that matrix equation. So let's go ahead and label the true solution to those. Let's just nail it down. It's sort of like somebody saying off to the side here that 3x equals 6 has a solution. The solution is not x. The solution we know is going to be 2. So we're not saying that x is the solution, it's 2 is the solution. We just haven't stated it out loud. Just like with this matrix equation right here, if we say ax equals b has a solution, we haven't actually stated the true solution yet. We're just saying whatever that variable is, x, we know there's something we can plug in to make this equation true. And that something we plug in will have entries, x1, x2, all the way to xn, that will be replaced to be some constants to make this equation true. So let's write down the sample solution here. There we go. There's our sample solution. We're supposing it's just some vector c, which has entries c1, c2 to cn, which by the way means that, because that solves a matrix equation, it also solves the vector equation. That is, when we plug it in to that asterisk equation up here, the vector equation, we get an identity, or what we would call a truth statement, that this left-hand side is equal to the right-hand side. That is, B is a linear combination of the columns of A, because remember, each one of these vectors is a column vector of A. So B is a linear combination of the columns of A with weights C1, C2, all the way to Cn. That is actually the forward proof. We have proven that the matrix equation having a solution will imply that the right-hand side, B, is a linear combination of the columns of A. We have finished that part of the proof. So now we're going to go the backward way. And often people find it better to write down what these ways are off to the side. So the forward direction's not that difficult to just see, but the backward direction's a little bit more challenging. So let me go ahead and showcase the backward direction. So the backward direction, we're going to start with the yellow highlighting. We're going to assume that the vector B is a linear combination of the columns of the matrix A. And then we will want to prove the blue highlighting, that the matrix equation AX equals B must therefore have a solution. So let's go ahead and assume the yellow highlighting. Suppose that the vector B is a linear combination of the columns of A. And LC is a very common shorthand for linear combination. It's just much faster than writing linear combination. Well, what does that imply? What do we know if B is a linear combination of the columns of A? Very simply put, we know that the vector B is the sum of scalar multiples of the columns of A. And I've written it as that the vector B is equal to C1 A1 plus C2 A2 all the way to Cn AN. There should be a plus in front of there. For some scalars C sub I, where C sub I actually could be real or complex, but in linear algebra, we generally deal with real valued coefficients, so we'll just pretend as though those are real valued numbers. Now, what does this mean that the vector B now is a linear combination, is a concrete linear combination, by the way? There are some scalars, C1, C2, all the way to Cn, that will make that statement true. But what does that imply so that we can get to the punchline, which is that the matrix equation AX equals B has a solution? Well, I would like to trade out those scalars C for X's so I can eventually get to AX equals B. Well, the fact that B is a linear combination of the columns of the matrix A, well, that tells us the following equation has a solution. Specifically, the solution is just C1, C2, C3, all the way to Cn. We know that, but this is important because we have a theorem, specifically the theorem that we had just introduced in the previous video, which is Theorem 3 in the text that I use, that says that the solution to a vector equation is the same as the solution to the associated matrix equation. Hence, by that theorem, which in my textbook is Theorem 3, the matrix equation AX equals B also has a solution, and by the way, that solution is just incidentally the same solution to the vector equation. It's the C1, C2, C3, all the way to Cn. So again, what we have proven is that if, in the yellow highlighting up above, B is a linear combination of the columns of A, then, the blue highlighting, the matrix equation AX equals B has a solution. So we have proven both directions. So this proof is completely done. QED, quod erat demonstratum. So it has been proven. So this video again was just focused on that single theorem, which is, I think, in many ways very natural for students to think of. At this point, they automatically kind of think this is true, but this is the actual proof of why it's true. And it's a good discussion of the if and only if, that it can go both ways. By the way, the if and only if, actually with any theorem you've been introduced to also has a contrapositive form. So not only is this an if and only if, but you can look at its contrapositive. Normally with a claim, a theorem, in mathematics, it has the structure if-then, if P then Q. The contrapositive will also always be true. That is, the contrapositive has the form not Q implies not P. Well, if the first statement is true, if P then Q, if that's a true theorem or a proved theorem, then the contrapositive, not Q implies not P, will also be a theorem. Think of it this way. If it's raining, then it's cloudy. So P is the fact that it could be raining, and Q is the claim that it is cloudy. If it's raining, then it's cloudy. The contrapositive, well, because we know that statement's true for most situations, except for very odd situations, right? So if it's raining, then it must be cloudy. That statement seems to be true, so let's just go along with it. The contrapositive would also have to be true. That is, if it's not cloudy, then it's not raining. That's just a different way of stating the original theorem, but the contrapositive statement is often very powerful. So every theorem you've ever learned in mathematics is actually a two-in-one. You have the original theorem, the if P then Q, and then you have its contrapositive. Not Q implies not P. In this case, if you just look at the forward direction, if the matrix equation has a solution, then B is a linear combination of the columns of A. The contrapositive says, hey, if B is not a linear combination of the columns of A, then the matrix equation AX equals B doesn't have a solution. That's a truth statement. And because it's an if and only if, it goes backwards too. That is, if the matrix equation AX equals B does not have a solution, then B is not a linear combination of the columns of A. So I'll write the contrapositive if and only if here as well. Not that that is something that you'll use. Actually, I think you do use it every once in a while. So let's go ahead and state this in contrapositive form as well. All right, in the red ink, the matrix equation AX equals B does not have a solution if and only if, that's what IFF means, if and only if the vector B is not a linear combination of the columns of A. So that's another way to state that theorem. So this is really a massive theorem with another interpretation, right? Our contrapositive interpretation. And it can be very powerful used in the contrapositive. So if you know that you have a vector that's not a linear combination in any given way of the columns of A, then there's just no solution to the associated matrix equation. It just can't be, because there's no way to get B from A times X, because again, B is not a linear combination of the columns of A. All right, I think I've talked in circles enough. I hope this video helps you out. I hope you have great luck and success in your linear algebra course, and I hope to see you in future videos. Have a great day. Be wonderful human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.